We just finished a demonstration, a couple demonstrations, in fact, where we showed you what happens when a wave encounters a boundary between two materials or between two media. We can get two things happening. In fact, we always get both of those things happening: reflection and transmission. Reflection means that it bounces back. Transmission means that it keeps going. When a wave encounters the boundary, some of it will always keep going, and some of it will always get reflected. If the two materials are real similar to each other, close to the same, then most of it's going to get transmitted. If they're very different, like in the demonstration that we did with slinky and person was the second medium, or slinky and air as the second medium, then most of it's going to get reflected. We're going to focus first on what happens to the part that gets reflected. If they're real similar, only a little bit gets reflected. If they're real different, a lot gets reflected. But the part that gets reflected behaves the same way regardless of whether most of it is getting reflected or only a little bit is getting reflected. So let's take a look at that now. Think back to the demonstrations that we did a second ago in the classroom and in the atrium. When was the wave reflected upright? When was it reflected right side up? When did it come back on the same side that it went down on? If you had a crest, when did it come back as a crest? Yep. Okay, when nothing was touching the other end of it, so when slinky was going to air, when it wasn't attached. Okay, you could also think of it as when it was going from more dense to less dense. So we're going to say when wave goes from more dense to less dense. And we're going to say that that happens, generally it happens when it's not attached to the other end. So when it was just hanging in the air, it wasn't attached, and there you could see that it was reflected right side up. It gets reflected inverted in the exact opposite scenario, when the wave goes from less dense to more dense. And generally that's going to happen when the wave or the medium that the wave is in, like a slinky for instance, is attached to the other end. So when Nick was holding on to the slinky, was reflected up, right side up, just so you remember this, kind of think back to the demonstration as you have a test or a quiz. When the wave was going from slinky to air, and it was reflected inverted when it was going from slinky to Nick. Yep. NIC, sorry, Nick NIC. Now I couldn't demonstrate for you the law of reflection. But you know what, even when you were 8 years old, you knew the law of reflection. You may not have been able to verbalize it. You may not have been able to formally tell me what the law of reflection was, but you intuitively knew what the law of reflection was. Everybody's played pool, right? Billiards, pool, at some point in their life. Some of you are good at it, some of you are not good at it. But everybody knows some of the basic principles of physics on which pool is based. Let's say you got the bumper of a pool table right here. And you got whatever pool ball right here, and you're hitting this one, this blue one, and you're trying to hit it around the black one. When you're 8 years old, you know intuitively that when you hit it off of the bumper at this angle, that it's going to bounce off about like that. Again, you know intuitively that the angle of incidence, we're going to call it theta I, as measured from a normal line. What does normal mean in physics? We have to have a fancy term for everything, right? What does normal mean in physics? Where have you heard that before? Yeah, normal means 90 degrees. So normal line is a line that's drawn 90 degrees to the boundary. A normal force was a force that was drawn at 90 degrees to the surface, right? The angle of incidence as measured from the normal line, theta I, is equal to the angle of reflection as measured from the normal line. In other words, theta I equals theta R. When you were 8 years old, you wouldn't have said theta I equals theta R. But when you were 8 years old, if I asked you to predict where that ball would go, you probably would have told me right there. Because you knew at some level the angle of incidence equals the angle of reflection. Now, this doesn't take away from what you just learned about right side up or upside down. I can't demonstrate this with a slinky, but this wave, if I could demonstrate it with a slinky, this wave would be reflected upside down if it's going from less dense to more dense, and it would be right side up if it's going from more dense to less dense. It would just be reflected at the same angle, that's all. So what happens to the part that gets transmitted? What happens to the part that keeps going? Well, I want to draw a picture for you to describe an analogy here. This is going to be the boundary between a paved parking lot and a swamp. So right at the edge of the parking lot is this swamp with maybe a half a meter of water in the swamp. For whatever reason, there's a bunch of soldiers in this parking lot. Like this. If we're in a helicopter or something, a high building, looking at them from above, it may look like the front of a wave. Kind of look like they're all kind of one, joined together. Now, soldiers march, right? That's what they do. They march, and they march in stride. So 5 seconds after they're in this position, these soldiers will be in this position. They're all marching in stride. They're all marching at the same speed. Hey, if they weren't, then it wouldn't look very good, right? They'd be all over the place. This guy, however, just starting to go into the swamp. This guy definitely in the swamp. They slow down, right? You can't walk as fast in a half a meter of water as you can on pavement. So they've slowed down. Let's join the lines now, or join the dots now. 5 seconds later, soldiers are up here. Except this guy, who's now in the swamp and is slowing down. This guy who's in the swamp, this guy who's still in the swamp, going to look something like this. 5 seconds later, this guy's now in the swamp, this guy's in the swamp, this guy, and this guy still in the swamp. So it's going to look something like this. The wave front, if we think of it as a wave, was traveling this way. Now it's traveling this way. When a wave goes from one medium to the other, what changes? Tell me, what changed here? There's 3 things. What's one of the things that changed when the soldiers went from the parking lot to the swamp? Yep. The speed. And the speed is the big one, because the speed is what causes everything else to change. The speed changes. You can speed up or slow down. In this case, it's slowed down. But if you were going from swamp to parking lot, the speed would increase, right? The speed changes. What else changes as a result of the speed changing? One of them staring you right in the face. What do you mean in the distance? Good, good. The wavelength. Look at this. Look at this distance between 2 waves. Look at this distance between 2 waves. The wavelength decreased there, right? So because the speed changed, the wavelength also changes. Good. What else? The direction changed. The angle changed, right? Now, I'm going to put a little star by direction, because in this case, clearly direction did change. But if the wave encountered the boundary straight on, right, the soldiers were marching straight into the swamp, they'd slow down, the wavelength would change, but the direction wouldn't change there, right? They only change direction if they go in at an angle. So the wavelength, the speed, and the direction can or will change. What stays the same? We alluded to this last week. One property of the wave never changes. Whether it's reflected, whether it's transmitted, no matter what, one property of the wave never changes. What are we missing here? What's not up on the board right now? Okay? The frequency. The frequency of this wave is always going to stay the same, no matter what. Now, in the end, if we relate this all to the wave equation, if the frequency doesn't change and the speed increases, then the wavelength must increase. Or if the frequency stays the same and the speed decreases, then the wavelength must decrease as well. All right? We'll leave it there for today. You got a few minutes left over here, about 4 or 5 minutes left over. You can work on those check and reflect questions that I assigned earlier for homework. If you finish those, you're good to go. If not, work on those questions. Okay? Otherwise, you're done.